On one blue world, glass rains sideways at 5,000 mph. The immediate takeaway is this: it is a real exoplanet. Its name is HD 18973b, a hot Jupiter. It orbits an orange star, 63 light-years from us. People call it an ocean of glass world. Here is what that actually means: airborne shards, not beaches. Silicate vapor condenses into glassy grains, then storms fling them sideways. Supersonic winds whip those grains, carving a blue, scouring sky. If you could stand there, you would not last seconds. Today we will tour this world piece by piece. By the end, oceans of glass will make clear sense. Picture a gas giant skimming so close, its star fills the sky. HD 18973b is that world, a hot Jupiter. Hot Jupiter means Jupiter-sized but cooked by a nearby star. You care because proximity rewrites weather, chemistry, and even day-night cycles. The planet circles its star every 2.2 Earth days. Tidal forces lock one side to daylight, one side to darkness. That fixed heating drives violent winds and shifts the hottest point east. Mechanically, sunlight pumps energy into upper air, building extreme pressure gradients. Air races toward night, but the planet's spin deflects the flow. The result is one dominant jet stream, roaring around the equator. Example: in real terms, that jet can approach 2 kilometers per second. For scale, commercial jets cruise at 250 meters per second. In telescope light, we see the planet's glow offset from noon. That offset maps the wind and confirms the locked, broiling dayside. Nightside temperatures stay scorching, still near 900 to 1000 Kelvin. So the picture is simple: close orbit means permanent jet-driven extremes. Clouds form and shred in that conveyor, seeding the next storm. Bottom line, proximity turns a Jupiter into a raging heat engine. There is a reason this planet looks deep, electric blue. Blue here is not water, it is scattered starlight by haze. Silicate vapor makes the haze, which is basically glass and gas. You should care because color encodes chemistry and reveals weather patterns. Sunlight hits tiny grains, shorter blue wavelengths scatter more efficiently. Larger red wavelengths pass deeper, where heat gets absorbed and re-emitted. That combination paints a blue disk, even though oceans do not exist. Grain sizes matter, think tenths of a micron for strong Rayleigh scattering. Grains condense on the night side, then ride winds back into daylight. Passing through warmer layers, droplets soften, then harden again as glassy beads. Example: in real terms, Hubble saw the color swing with wavelength. Blue light dropped strongly, near 450 nanometers. That drop fits silicate haze, not ocean water or methane clouds. So the picture is sky blue from glass dust, not seas. Ground-based spectra also show sodium absorption, consistent with a hot atmosphere. When clouds thicken, albedo rises slightly and the disk brightens toward blue. Tiny test: would thicker grains redden or blue the disk more? Thicker grains scatter longer wavelengths, so the scene would mute blue. Bottom line, the color is a chemical fingerprint of glassy skies. Now think about the wind, not breezes, but planetary scale jets. Supersonic means faster than sound waves can travel through air. This matters because supersonic flow carries brutal energy and shreds clouds. On HD 18973b, winds approach 2 kilometers per second. That is about 4,500 miles per hour, give or take. Local sound speed in hot hydrogen is comparable, roughly 1 to 3. So parts go near Mach 1, other flows likely exceed Mach 1. Mechanically, day-night heating drives pressure waves that wrap the equator. Coriolis twisting steers those waves east, stacking momentum into a jet. Friction stays weak aloft, so the jet just keeps accelerating. Deep layers drag slower, while upper layers race far ahead. Example: in real terms, hotspot maps sit 30 degrees east of noon. That offset is exactly what a super-rotating jet would create. High-resolution spectra also show windward Doppler shifts in carbon monoxide lines. The lines slide by a few kilometers per second, matching models. One-sentence recap: winds here beat most earthly bullets to the horizon. Grains caught in that stream become sandblasters, polishing clouds to shards. Bottom line, supersonic jets are the planet's main climate machine. Here is the sneaky part: we have never seen the surface. We infer everything from light, sliced, timed, and compared across colors. Transit dips reveal the planet's size and even hints of haze. Secondary eclipses show the dayside glow when the planet slips behind. This matters because timing and color together build crude weather maps. Phase curves track brightness through an orbit, revealing hotspot positions and winds. Hubble measured blue scattering, Spitzer mapped temperature patterns at infrared wavelengths. Ground spectrographs used Doppler shifts, reading wind speeds inside spectral fingerprints. JWST now resolves molecules like water, carbon monoxide, and possibly silicate features. Example in real terms, the orbit is 2.2 days. The depth of transit is roughly 2% of the star. Secondary eclipse depth registers near 0.1% in infrared bands. Those tiny signals, stacked carefully, become weather inferences this crisp. So the picture is, precision photometry lets us read alien skies. Rule of thumb, brighter before eclipse means the hotspot sits east. Cross-correlation tricks amplify faint lines, giving wind vectors and chemistry. Bottom line, telescopes turn flickers of starlight into climate reports. We never touch the planet, yet we chart storms with numbers. So about those oceans of glass, the phrase sounds literal, right? It really means silicate rain, glassy droplets falling through a storm. You care because words shape intuition, and this world deserves accuracy. Silicate vapor forms high, then cools on the dark side into droplets. Those droplets can harden into small glass particles, essentially airborne sand. Winds carry them sideways, so rain falls nearly horizontal, not downward. Think sandblasting but planet-wide, powered by a star-warmed engine. The grains likely measure tenths of microns, small yet vicious in swarms. Example in real terms, cloud bases might sit near a bar. Updrafts loft particles higher where they catch jets and circle endlessly. No beaches here, only suspended glass flowing like liquid from afar. Lightning may spark in those clouds, charging grains and boosting collisions. Charged grains stick briefly, then shear apart, making even sharper fragments. Radiative heating softens them again, so the cycle repeats without end. A human visor would sand to frost in seconds, visibility gone. Spacesuits would fail quickly, torn by impacts and heated beyond survival. Net result, oceans of glass describe skies, not solid seas. Bottom line, the phrase is poetic shorthand for savage airborne glass. Zoom out to the whole globe and a pattern snaps into view. Superrotation is the name for that eastward equatorial jet. It matters because a single jet reorganizes heat, chemistry, and clouds worldwide. Wave trains born at the day-night boundary migrate and deposit momentum eastward. Frictional drag in deeper layers slows return flow toward the west. Up top, thin air loses little energy, so it outruns everyone. The jet shifts the hottest spot, moving at 30 degrees east. That shift changes chemistry, baking molecules longer before they meet nightside cold. Example with numbers, wind speeds likely span 1 to 3 kilometers per second. Vertical shear stacks layers, with deep flows lagging and upper flows ripping. Cloud tops may migrate seasonlessly, because seasons barely exist here. One sentence recap, a single jet rules weather across the globe. Storms probably anchor near the terminators, where heating gradients stay strongest. Lightning, shocks, and vortices feed the jet, keeping momentum supplied. Bottom line, rotation and radiation together sculpt one continuous river of air. Let us anchor this with comparisons, so the scale really lands. Sound in Earth's air moves near 340 meters per second. Hurricane winds top out near 90 meters per second, Category 5. On this planet, winds push 1,000 to 3,000 meters per second. Tiny test, which is faster, the wind or a rifle bullet. Many bullets fly near 800 meters per second, so slower. Another anchor, Earth sandstorms erode paint in minutes and glass in hours. Grains here would pit metal instantly and shred composites without mercy. Power from the jet is enormous, roughly 10 to the power of 15 watts. That rivals multiple hurricanes running together without pausing to rest. Example in real terms, full planet circulation completes in mere hours. Thermal contrasts add fuel continuously, so there is no calm season. Cloud height changes faster than Earth jet streams because heating swings faster. Net result, the planet runs a perpetual storm lab at colossal scale. Bottom line, this world makes our worst storms look quaint, almost gentle. Why should we care beyond the spectacle? Because this is climate physics. Hot Jupiters are test beds, letting us stress test models against extreme data. That matters for cooler worlds too, including future Earth-sized discoveries. We learn how winds move heat, how clouds seed, and how spectra respond. JWST now pulls phase curves in multiple bands, mapping chemistry by longitude. Ariel will survey hundreds more, building a library of alien weather. Extremely large telescopes will resolve wind maps directly, with sharper Doppler lines. Example with numbers, JWST spectra show water features at parts per million. Combine those with timing and you get moving chemistry across longitudes. That crossover between dynamics and chemistry will guide searches for habitability. One sentence recap, glass storms today teach us to read tomorrow's skies. Bottom line, weird worlds are not sideshows, they are roadmaps. We also test retrieval techniques, comparing models against real, messy signals. Better retrievals mean fewer false positives when biosignatures eventually appear. And frankly, it is a reminder that nature out-imagines us. Net result, curiosity here upgrades the tools that read every other world. That blue world with sideways glass rain is not a rumor. It is HD 18973b, storming as we speak. Oceans of glass turned out to be skies, scoured by supersonic winds. Now you know the mechanism, the numbers, and the evidence behind it. If this kind of cosmic weather fascinates you, there is more coming. I cover new observations and the wild physics they reveal. Subscribe to catch the next storm map and bring a friend. Bottom line, curiosity is the best pressure suit for alien skies. Thanks for watching and for exploring this strange blue giant with me.